At this point, we have talked about chemical reactions, how to balance them, and what the 5 types of chemical reactions are. Now what we're going to talk about is a practical application of those chemical reactions. If we want to conduct a chemical reaction in lab, we can't talk about atoms or molecules, but we can talk about grams and volume. So now we're talking about calculations of quantities in chemical reactions. So the first thing we need to do is go back and visit the concept of a mole. Now remember, a mole is a huge number, 6.02 times 10 to the 23rd. Why do we care about using the concept of a mole? It's because atoms are so tiny that when you want to do a chemical reaction in lab, we're not going to talk about reacting one atom of an element with another atom. We can't do that in lab. We can only measure things in grams and liters for volume. So we're going to scale everything up, and instead of talking about atoms and molecules, we're going to be talking about moles. So one of the things we had talked about was this whole concept of mole. One term we had talked about was GMM, gram molar mass, or gram formula mass. Mass, you basically add up all the masses of all the elements in a given compound. The other thing we had talked about was this number, 22.4 liters. We had talked about how 1 mole of any gas whatsoever, has a volume of 2 point or of 22.4 liters at STP. Now, STP stands for standard temperature and pressure. The exact values for standard temperature and pressure are given in the periodic table in the first table, table A. So now what we're going to do is remind ourselves again about mole central station. So here's our simple mole central station where you have mass in grams, volume is in liters, and remember, number of particles are atoms or particles, etc. This is your mole in the middle. Remember, if you're going between moles and grams, you're going to either multiply or divide by GMM. GMM units are grams per mole. Here you're either going to multiply or divide by 22.4 liters. Again, the correct unit is 22.4 liters per mole. And here you're going to multiply or divide by Avogadro's number, which is the 6.02 times 10 to the 23rd. In this case, it's atoms or molecules per mole. So this was our mole central station. When we start talking about chemical reactions, we are not really going to care about number of atoms or molecules anymore because we're talking about actually conducting these experiments in lab. So what we're going to be doing is we are going to disregard this portion of it, and all we're going to talk about is the conversion between moles to mass and moles to volume. So first of all, let's try doing a problem, and the first thing we're going to do is balance a chemical equation. Now this one is a little bit trickier than the ones we've done in class, so let's start and see what we get. First, we're going to balance the carbons, and we should get 2 carbons on both sides. I have 6 hydrogens here, so I need 3 over here to make it 6 oxygens. At this point, I have 4 oxygens and 3 oxygens. Now I have 7 oxygens. How could I possibly make that into a whole number and still get an even number because you're multiplying it by 2? So here's a trick. You can write it as 7 over 2, 3/2. Obviously you can't have 3.5 atoms or molecules. You don't want a denominator in here. So if I multiply the whole entire equation by 2, I would get 2. 7 over 2 times 2, 7. 2 times 2, 4. 3 times 2, 6. So my correct coefficients now are 2, 7, 4, 6. So what do these numbers actually represent? Well, it looks like it's going to show us that 2 molecules of C2H6 react with 7 molecules of O2, and as a result we get 4 molecules of CO2 and 6 molecules of water. again, we're trying to scale everything up for a chemical reaction. So do we really care whether it's molecules or not? Not really. So these coefficients that are used in balancing equations represent not only number of atoms or molecules used in the reaction, but also number of moles. So if I scale everything up, I can say 2 moles of C2H6 react with 7 moles of O2, and I get 4 moles of CO2 and 6 moles of H2O. Now, using these, we can write any kind of a ratio. What this tells us is that for every 2 moles of C2H6, I can make 6 moles of water. Or for every 7 moles of oxygen I use, I can get 6 moles of water. These numbers right here, the coefficients, give us mole ratios. And again, I can have any kind of mole ratio I want to be represented. Here are some examples. Again, 2 moles of C2H6 for every 7 moles of O2. 4 moles of CO2 for every 7 moles of O2, etc. So you can have whatever different ratio that you want in there. So now let's see how that would relate to a problem. Here again we have the same problem. So here's the 2, 7, 4, 6. How many moles of water will be produced from the complete combustion of 3 moles of C2H6? So we're talking about C2H6 and water. If you look from the balanced chemical equation, the ratio of C2H6 to water is 2 to 6. So according to my balanced chemical equation, for every 2 moles of C2H6, I get 6 moles of water. So now the question is, well, what if I have 3 moles of C2H6? How many moles of water would I form? So you can just set up a simple ratio. Now the easier way to set up the ratio is this. You can write whatever you know, the known, above the formula. So you could put a 3 moles here. And the unknown, you're looking for moles of water, you can put an X over here. And this right here sets up the ratio for you. 3 over 2 equals X over 6 from here. Again, the basic concept is this. For mole ratios, you can balance the chemical equation first, write the known and unknown above its formula, and set up the ratio of moles. That is going to be the simplest way to do it, because these numbers already represent moles, and you are either given or looking for moles. So let's try a problem. First thing again you have to do is balance the chemical equation. So let's do that first. 2 nitrogens, 6 hydrogens, so I need a 3 here. Make sure you check everything, and everything is balanced right now. Now, how many moles of H2? So as soon as you see that, there's your question. You're going to put an X moles above H2. Are needed to produce 7.24 moles of ammonia. So here I'm going to put 7.24 moles of ammonia. And I can set up the ratio right there. X over 3. Now these are moles of H2 over, on the other side we have 7.24 over 2. These all represent moles of ammonia, moles of ammonia. This is how you would solve the problem. So now we have X. X in this case is going to be equal to, it's going to be equal to 10.9 moles. Now in this case you want to make sure that you are not only writing down the unit, but also the name of the formula itself, because you have 3 different things you could be talking about. So you want to make sure you put the correct units and the correct formula. So here's one more for you to try. This time we have how many moles of nitrogen are needed to produce 7.24 moles of ammonia. So now the only difference is that we are changing the X. where the X is. So 7.24 moles of ammonia is still there, 7.24 moles, and the X now is above N2, X moles. So now your ratio would be X over 1 equals 7.24 over 2. I don't care if you put the units here or not, but again, make sure that you have the correct units at the next step. So in this case, you would get 3.62 moles of N2. Unit and compound are very necessary. So if you're working with moles, it's as easy as that. Just write the known and unknown above the formula and set up the ratio. Now, what about if you now have an equation? So here's my equation, and remember mole central station. Now, first of all, what we're going to do is this. Since particles don't really come into play, we're just going to get rid of that part. So now all we're talking about is this part of mole central station. Here's moles, volume, and mass. Now here obviously you're going to have some numbers from the balanced chemical equation. So what you want to think about is this. Picture that for each one there's a mole central station, because the numbers up here represent moles, and those moles can be converted to mass or volume, mass or volume. Mole central station here is individual. It is specific to each element or compound. So it is specific to each element or compound, whether it's A, B, C, or D. So you can't just say I can use mole central station for here and here together. The connection you have between these compounds is this mole ratio. So let's take a look at the next type of problem. Here it says how many grams of LiBr are formed when 42 grams of lithium react with bromine. So first of all, I'm talking about LiBr and I'm talking about lithium. The number for lithium is given, and we're looking for grams of LiBr. So think about mole central station for this and a mole central station for this. Now let's look at what values are given to us. 42.0 grams of lithium. So grams, that means we're here. 42.0 grams. I'm looking for grams of LiBr, so my X is here. So now consider this. You have to go from grams to moles. This right here is going to be your mole to mole ratio from the balanced chemical equation, is your connection from lithium to LiBr. And then you would have to go with this arrow to get to the mass. Just think about a kind of like a map. So here I have, if I have grams of X, first I need to convert them to moles of X. That's this arrow right there. And again, that has to do the relationship as with the GMM. Now we do the mole to mole ratio, and then we get to the GMM of Y. In this case, here is how you would do the problem. You would start with, so the question is how many moles, the question is how many grams, so how many grams of LiBr, that's what you're looking for, are in, and you're starting with 42.0 grams of lithium. Now you are going to look up the GMM, because this right here is a GMM, that's your connection. So if you look it up, 6.9 grams of lithium are in 1 mole of lithium. This is the dividing by the GMM to get to moles. Grams cancel. Now your connection is between lithium and LiBr are these two coefficients. So for every 2 moles of lithium, I get 2 moles of LiBr. That's from your balanced chemical equation. Moles cancel. I'm left with moles of LiBr. And now every 1 mole of LiBr has a mass of, and this is the GMM of LiBr that you would look up, which turns out to be 86.8 grams. Moles cancel. You are left with grams of LiBr. In this case, the answer turns out to be 804 grams of LiBr. I would like you guys to try this problem for tomorrow. Thank you.